Syzygy, episode 12, a bright question from a listener makes us think about light. And welcome back for another episode of Syzygy. This is episode 12. Joining me on the microphone, as ever, the wonderful Emily Brunsden. Hi, Emily.
Hello, hello.
So in this episode, it's very, very exciting. We're going to build the entire episode around a listener question. We've had a question in from friend of the show, Stuart Priest. Stuart, who is he's an interesting chap. He's been here at the university working in all sorts of areas for quite a long time. He's worked in high-performance computing. He's worked in the sciences, a biologist or a chemist, one of the two. I can never remember. But now he's out and about doing circus skills workshops with schools, and he mixes in a bit of physics in there to sort of show how gravity works when you're doing juggling and that kind of thing. Awesome stuff.
Very, very cool.
Yeah, if you see Stuart in the street, just give him a big shout out because it's great stuff. Anyway, Stuart got in contact with us through our webpage, which is syzygy.fm. If you go there, you can find the contact form, throw us a question like Stuart did, and we might answer it on the show. We might even turn it into an entire show.
We got so carried away today. It was so exciting.
We really have. So, Stuart's question was all about photons. He said, look, obviously, astronomy wouldn't be around if it weren't for photons, but what is the deal with photons? And in particular, what's the latest theories about them? What are they? But also, why is it that in a black hole, light can't escape the gravity of the black hole? And yet, from everything that we've ever heard about photons, they have no mass. And if photons have no mass, how can they be affected by gravity? Asks Stuart. So we're going to explore that in the show today. We're going to talk about photons. We're going to get right down into the nitty-gritty, probably get a little bit too into the weeds, actually, knowing us, but we'll see how we go. In order to try to answer this conundrum, how is it that light is affected by gravity? What is this light stuff anyway? And why is it so important in astronomy?
Astronomers just love light.
They do. But why? Why light? What makes it so special? First of all, photons. Emily, what's a photon?
What's a photon? That's a really, really good question.
I'm just going to throw that one to you.
It's not a very obvious and easy one to answer, actually.
It's not. So let's go with the broadest possible definition. When we say photon, what are we talking about?
So if you think about light as part of the electromagnetic spectrum, so this is this whole spectrum of light, which includes the light that we can see and all the other sort of colours and frequencies that we can't, radio all the way up to gamma rays. Then the photon is the smallest packet, if you like, the smallest quantum of that light, of electromagnetic radiation that we can have.
Now, this is going back to about 100 and something years ago, right, when there's sort of been a debate in physics for quite a long time about this light stuff, what is it? And I mean, I think it was Douglas Adams who pointed out in one of his books that, light travels so fast that it took human beings thousands of years to work out that it actually travels at all. You turn the light switch on and it's instantaneous. It's right there to you. And that's because it's a trick of the light. It travels so fast. And we're talking 3 by 10 to the 8 meters per second in a vacuum.
Yep, 300,000 kilometers per second.
Per second. It's so fast that it takes... How long for light to get from us to the moon? It's
only a few seconds.
It takes 8 minutes for light to get from the sun to us. I mean, it's incredibly fast, but finite in speed. And there's been a debate for a really long time in physics, hundreds of years, about, but what is it? What is this stuff? And for a long time, it was assumed to be, it must be little lumps of stuff, little, you can imagine little lumps, little balls of light stuff coming and hitting us. And then for a while it was, no, definitely not. Light is a wave. And this was codified really, really well by Maxwell, who brought together a bunch of ideas from a whole bunch of people about how electricity and magnetism works, brought it together as what we now call electromagnetism. And there were a bunch of equations that described electricity and magnetism and how all of that works. And it was a beautiful theory. But in amongst it was this little equation that said, yeah, but you know what? Electromagnetism should be able to create waves. If you wiggle electric charges around, then they should give off waves. And the theory actually gave us the speed of these waves. And what do you know? It was exactly the speed that we had measured light to be. So light is an electromagnetic wave. There's no question about it.
Yep.
And then 100 and something years ago, a couple of people came along and said, look, it's a bit more complicated than that. Sometimes light behaves like a wave, and sometimes light doesn't behave like a wave, and sometimes it behaves like a particle, and quantum physics was born, and everyone's heads exploded. But in quantum physics, sometimes you have to describe light like a wave, but sometimes you have to describe it like a particle. And when you're talking about light as a particle, you're talking about a photon.
Yeah. And I think one of the easiest things to misunderstand with light is that is it a question for debate? Is it just that we haven't worked out is it a particle or is it a wave?
Yeah, come on, physicists, get your act together.
Surely with a big enough experiment
one,
we can sort this out once and for all.
What are you doing with your time over there in the physics department? Yeah, but it's not that.
It's just not that. No, and actually you can have two experiments sitting side by side, and you can have one which shows that light is definitely a wave, it behaves like a wave, it does all the things that waves do, and then you can have the other one sitting right next to it, and light is a particle, it's doing all the particle things that particles do, and both are true.
Yeah, and not only that, you can have an experiment which shows that it's acting like a particle, but that some of the experiment shows you that particle's position, like say you've got a photon hitting a screen and making a dot on the screen, the position of where that photon ended up depends on it actually having acted like a wave along the way. It's a particle and a wave at the same time, and that's very confusing because that's not what we're used to. But one of the great arts of being involved in physics and theoretical physics, quantum physics particularly, is getting comfortable with that. And eventually, I can remember when I was an undergraduate student studying physics and wrapping my head around this. And one of our professors told us, look, you're going to get used to it, and that confusion's going to sort of go away for a bit, and then you'll think you'll understand it. And then 5 years later, your brain will fall apart again, and you won't understand anything, and you'll piece it all back together, and you'll understand it. And then 5 years later, it'll fall apart. So I don't think you ever completely get over that weirdness, but it becomes less weird.
No, and it's certainly something we can never visualize, this kind of object.
No. You find different ways of visualizing it, or at least being able to juggle. Here you go, Stuart, coming back to your comfort zone. Different ways of juggling contradictory and yet complementary ideas at the same time. Is it this? Is it that? Don't have to choose. It's both. Whichever works.
So in my mind, I have this very, very wrong picture, which comes from, I think, almost every introductory physics textbook ever, which is you have these little squiggles coming out of an object which is releasing light. And each of those squiggles is kind of in a packet, which means it's a particle of squiggles. It's completely wrong in almost every sense, but in some ways it kind of helps you move along this path of acceptance, if you like.
There's a lot of imagery in physics and in quantum physics which is wrong, not completely wrong. It's actually still partially right, but it's still wrong. It's still a bit right. Anyway, so that's photons. Let's back up a little bit. You can go down all sorts of rabbit holes on this. Photon is fundamental particle of electromagnetic waves, light. And when we're talking about light in this context, it's anything from the very long wavelength, very low frequency sort of radio waves, and right through to visible light, the Roy G. Biv visible spectrum of the rainbow, right through the other end to much higher energy things like X-rays and gamma rays and things like that. So it's the entire spectrum. It's all exactly the same stuff. And at its fundamental level, we talk about the particles being photons. The only difference being how much energy each individual photon has.
Yes, yep. That's what defines a photon. It's got some energy which is transferred, you can parameterize by either the frequency or the wavelength or both. So
that's what it is, but that's not what Stuart's question was. Part of the question was, so what's the latest on photons? That's still pretty much the latest on photons. Yeah. That's basically where we are. But at the heart of the question is, all right, smart people, how is it that photons can be influenced by gravity? So why is that even a question? Well, if you look at the way most of us are introduced to the concept of gravity, say in high school physics classes, high school science classes, it's about you pick something up, you drop it to the ground, and it falls. How do we describe that force? And you've got to go back several hundred years, back to Isaac Newton, who apparently, watching an apple fall from a tree, I don't know that that's actually true, but it makes a really good story, came up with a theory which showed that the acceleration of an object as it drops towards the ground is dependent on the mass of the object and the mass of the Earth. And he came up with an equation which is able to describe, based only on the masses of the two objects and the distance between them, what the force is between those two objects. The force of gravity, Newton's force of gravity. So that's all good. Excellent. Well done, Isaac. Nice work. However, that force depends on the mass of the objects involved. The force depends on the mass of the Earth. It depends on the mass of the apple, or of you, or of the moon, or whatever the other object might be. And so if you've got something like a photon, which has no mass, this is one of the other things about photons. It doesn't have any mass in the same way that an electron has mass, or a proton has mass. It has no mass. So how could it possibly be that photons could be affected by gravity?
Yes, now we're going to have to add a new little word in here.
Mm-hmm.
So a photon doesn't have any rest mass.
Mm-hmm.
Now this is where the important distinction comes from. Now Newton's gravity is very, very useful. It describes the everyday experiences that we have. It even describes astronomical situations like, say, the planets going around the sun.
It's really good.
It's very, very good.
We're not dissing Newton here in any way, shape or form.
No, but it's not the end of the story. And this is, unfortunately, the end of the story in, say, secondary school physics is basically Newton's gravity. But to understand photons properly with the gravitation, or at least what gravitation means for photons, then we need to pull out special relativity, which is Einstein's theory that comes from the beginning of last century when, at the same time as all these kind of things were coming out, this wave-particle duality, we had special relativity, and then later on general relativity.
It was a big time in physics, wasn't it, about 100 or so years ago?
Yeah.
When
Complete revolution.
Everything that we knew about atoms and light and space and time and mass and matter, everything just, you know what? No, none of that. None of that works. Throw it out, start again.
So instead of thinking about gravity affects objects that have mass, it's actually more correct to think about gravity affects things which have energy. And photons definitely have energy, right? We can measure it. It's based on the frequency and, it's a very straightforward equation, actually. It's the energy is equal to Planck's constant times the frequency. So it's very easy to calculate how much energy a photon has based on its frequency. And so even though a photon does not have any rest mass, which means if you stopped a photon from moving, it would not have a mass, which is a bit of a weird concept and maybe not something you want to try. But the fact that it is this packet of energy that's moving, then it has energy, therefore it's affected by gravity. And if we come back to Einstein's very famous equation, we do actually know that there's a principal relationship between mass and energy. They're related by this wonderful expression E equals mc squared. And of course the c in the c squared is the speed of light squared, and then E and m are therefore interchangeable.
Yeah, I mean, that was Einstein's sort of the first thing that he gave us in order to be able to see a way into this problem, the E equals mc squared, which is giving an equivalence between energy and mass. And it's the most famous equation you can possibly think of, I think. But where that comes into gravity is actually through Einstein's other great and more general look at gravity, which is his general theory of relativity, where he made that connection between the way that objects interact with each other through the force of gravity is actually about the way that space and time itself bending and warping around things which have a lot of energy, which mass is equivalent to through the earlier equation, then you get this warp of space and time, which means that anything which is traveling through space-time follows that warp. And so you can imagine the moon going around the Earth or the Earth going around the sun. You can imagine that as because it's being dragged down by the force of gravity towards the sun, the Earth's being sort of dragged around. Or you can think of it as it's just sort of rolling around a big curved surface around the sun, the curvature of that space, because the sun's so big and massive. And if the Earth's going to do that rolling, then light will as well. Light's just going to follow a curved path around curved space-time.
Yeah, the way I like to think about it, which is in the wrong number of dimensions, but kind of helps a little bit, is if you have like a massive checkered bedspread, and you've got sort of a grid on your bedspread, and then you're going to put a big heavy mass in the middle, say an enormous bowling ball in the middle. So you get a big dent in the middle of your bedspread. So instead of all those lines, those check lines being straight, now they're all kind of curved, right? And mass and energy, actually, well, so these anything that has energy, which is mass or energy, then they have to follow those lines. So they have to follow those curves as they go around that bowling ball.
Yeah, it does. It warps your head a bit, but this is the elegance of Einstein's general theory of relativity, is that it linked something which was very complicated and very confusing. It linked it to something very, very simple, which is geometry. You know, we're very used to, from quite an early age, as one of the earliest things that we start to learn about in mathematics is angles and straight lines and right angles and that sort of thing. You take that up a couple of notches and you get into, okay, yes, four-dimensional curved geometries and things like that. But it becomes incredibly simple in the way that Einstein put together, look, if you get this energy stuff and you connect it in this way to the geometry of the universe, you've got gravity. That's stunningly beautiful as a theory. So ultimately what we're talking about here is not so much that, wow, how is it that light with no mass can possibly be attracted by the force of gravity, which needs mass? No, it's not so much that. Light is traveling through space-time, and it's following a curved path like everything else. It kind of brings us to another point about all of this, which is the whole concept of mass. And I think it's worth spending just a minute, because mass is incredibly important in the universe as we observe it. Let's just think for a moment about this. There's two things about mass. And one is, why should we be so surprised that light, which, you know, as a particle, a photon, has no mass, why should we be surprised that that would be affected by gravity? Because if you walk outside and drop two objects, one very, very heavy and one not so heavy, they will be accelerated at the same rate down towards the ground. Okay, ignoring air resistance. You know, if you drop a feather and a bowling ball, yes, the feather will waft down. Ignore that. Take all the air away.
And we've done those experiments, and they're beautiful, actually, videos to watch. You can watch in a vacuum. You can watch a feather and a bowling ball fall at exactly the same rate. It's
absolute
just fun.
Cracker by Brian Cox, of course.
Oh, yes.
Yeah, gets the biggest vacuum chamber on the planet to do his experiments. But we'll link to that in the show notes. But you can do that, and that means that the acceleration down towards the Earth is exactly the same. Doesn't matter what your mass is. So if you follow that to a logical extreme, maybe it's not so surprising that something which has no mass still follows that same law, which is it'll be accelerated. So that's one thing. Just leave that with you. The other thing is, what is mass anyway? And that's a very, very deep question. But I just wanted to throw this one in because I was thinking about it earlier this morning. If you look at a proton, right, one of the particles that makes up an atom, in the nucleus of an atom, it has a certain mass. It's a lump of stuff. A proton's made up of things. A proton's made up of quarks. And those are little lumps of stuff. But the mass of the proton is less than 1% made up of the little bits inside it, the quarks inside it. The rest of it is the energy of all the gluons inside there, which are the things that are holding it all together. The mass of the proton is mostly the energy of the stuff inside. And so once you start thinking about that, you start to think, why are we so hung up on this whole mass thing anyway? We don't even understand what this stuff is. It's very, very complicated. So the best way to think about it, I think, is don't worry about mass. If something's got energy, it's going to be influenced by gravity.
Yep. And we'll throw one last thing in there just to warp your mind a little bit more. So photons do not have any mass or no rest mass, but they also have momentum.
Oh, photons are going to do your head in, I think.
Yep. So you could put your arm out, if you were sensitive enough, you could put your arm out in the sunlight and feel all the momentum of all the photons hitting your arm.
So, okay, I think we probably... Stuart, do you reckon? Have we done that one to death? I think we probably have. The first part of the question that Stuart sent to us was photons. What would astronomy be without them? That's a perfectly valid question. Emily, where would we be without them?
I can probably fairly confidently say it wouldn't exist. So in astronomy, we're used to this idea that astronomy is looking up at the night sky. We can see stars, galaxies, all these lovely things that we can take photographs of. And of course, there's all the invisible astronomy. So this is using the parts of the electromagnetic spectrum that we can't see. So infrared astronomy, ultraviolet astronomy, all these other types of astronomy using invisible light to us, at least, but our detectors can see it. But that's all still light. So these are all still photons. Photons are not 100% of the story, although they're very, very close to 100% of what we learned. But we have two brand new techniques in astronomy that use not photons from the universe, but other things. So the first one, which is a little bit older, is neutrino astronomy. So neutrinos are very, very tiny particles that are produced by the sun. They're produced in supernova, things like that.
They're produced in nuclear reactions, aren't they?
Yeah.
And so if you've got, for example, there's a lot of neutrinos coming from the sun because there's an enormous amount of nuclear stuff going, nuclear fusion going on down in the core of the sun, which is releasing a lot of energy, hence, the sun, but also releasing a lot of neutrinos.
Yes, so neutrinos tell us a lot about nuclear reactions and what's going on, and we can detect them. Although when we dig into the details of how we detect neutrinos, we actually look for light that's produced from the collisions of neutrinos with other things.
So it's not even completely divorced from the whole light thing. It's just that you're looking for neutrinos, but you're still using light to find them.
Yeah. Okay, so that field would still be not really applicable to...
And it's really interesting also because you said that's a fairly new kind of astronomy. And the reason why it's so new is because neutrinos are so ghost-like that they're actually really, really, really hard to find.
They definitely deserve a whole episode just on neutrinos.
They do.
They're very exciting.
They're so hard to find because they interact so little with ordinary matter that there are, extraordinary numbers of them passing through us right now. And in our lifetimes, maybe a few will interact with the atoms in our body out of the countless billions and trillions that pass through us. And so it's taken a really long time to actually build the technology to be able to see these suckers, let alone figure out that they exist in the first place. So there's neutrino astronomy. What's the other new one?
Well, gravitational waves.
Oh, yes, of course. Very exciting.
Very, very, very new. Now, so gravitational waves we've been detecting from astronomical objects. Then it's not light. It's actually ripples in this fabric of space-time that we've been talking about. So these kind of the duvet, if you like, is now rippling, and we can detect that.
Yeah,
that motion.
in a nice parallel to the way we were talking earlier about light being a ripple in the electromagnetic field, if you want to think of it that way. The equations that Maxwell came up with showed that you should be able to produce these electromagnetic waves, and that's light. Einstein's equation said, well, not only can you warp space-time, but you should be able to actually twang it as well. That you should be able to have an energetic enough event that will make space-time ripple and send out waves, gravitational waves. 100 years ago, he produced that idea, and it's taken until, when was it, 2015?
Yeah.
2015 to actually detect them, because they're, again, here's a whole other episode. They are so incredibly small, these ripples, that it took until the last couple of years to be able to create a sensitive enough detector to be able to actually see them at all. But now that we have, what does that do for astronomy?
Well, it changes the astronomy a bit, but and we're definitely going to talk about this in a future episode because gravitational waves are so exciting.
Yeah, put a sticky note on that one.
Yeah. So we can get signatures from events that we would never be able to see with ordinary light. But let's go back to how we detect gravitational waves again. We use lasers.
It's always
which okay. Have photons, yeah.
Why is it? So here's a question. Why is it that light is so useful in astronomy, right? You've just mentioned two really, really difficult new forms of astronomy, neutrinos and gravity waves, both of which took decades, if not a century, to figure out how to actually detect them at all. Light has been used in astronomy since people first looked up. You know, we can see stuff in the night sky. All we have to do is look a bit harder or with different wavelengths. Why is light so good? What makes light such a useful thing in astronomy?
It is. It is a brilliant, brilliant tool. And we are so lucky that light behaves the way that it does. And it does travel through different things to get to us. So say the light is emitted from a star, it will travel through some medium in between us and the star. It'll pick up signatures from that medium. But obviously the techniques that we have now for examining this light are continually getting better and better by orders and orders of magnitude. But it's nice to think about light as this kind of very fundamental thing we've been using forever, but we still don't quite understand all the details.
Well, from a physics and from a mathematical point of view, there's a really deep and interesting reason why as well, that light and electromagnetism is a very long distance phenomenon. It's a very long distance force. Mathematically, the equations, the law of that force, the force law, goes as 1 over r squared. So if you're not into equations, just ignore that bit. If you are into the maths, one way of thinking about that is that the strength of the force falls off as you get further and further away by 1 over the distance squared. In practice, what that means is that light and electricity and magnetism can act over very, very long distances. And we know that, you know, you can get a magnet in your fingers and another magnet in your other fingers, and you can feel that distance across centimeters. Here I'm bumping the microphone, I'm getting excited. Feel that across centimeters of distance. That's a really long way in terms of the atoms in those things. Right up to the light coming from the sun traveling across huge numbers, or across the galaxy, or across from other galaxies. It's a very long range force, is electromagnetism. As opposed to the nuclear forces, which is how neutrinos interact. Those nuclear forces are incredibly short range, like fractions of the size of an atom across which those forces would act, which means that they have to get incredibly close together for anything to happen, which is why so many of these things can travel through you, never interacting with you whatsoever. You're invisible to neutrinos vast majority of the time, which makes it really, really hard to use for astronomy, because if you can't see them, then you can't use them to look at stuff unless you get, you know, some incredibly big and expensive and incredibly finely tuned experiment to do so. Gravity is interesting because gravity is also a very long-range force, got the same kind of force law as electromagnetism. The problem with gravity waves is that they're so small. They are so incredibly
really
weak.
tiny.
It's a bit like if all the light from all the stars and the galaxies and the planets were millions of times fainter, then we may never have even noticed that they were there at all. Yeah. You know, you look up into the sky and it's just black until eventually you find a way to be able to see these incredibly dim objects. That's a little bit what detecting gravity waves is like. So, yeah, we're lucky to have light, really.
Yes, but we do have to look after our light.
Well, yeah, that is true, actually. And speaking as an astronomer, you've got a few dollars in this particular game, haven't you?
Yeah, but I think culturally, actually, as humanity, we have to look after our dark skies particularly. It's been the case in astronomy for a very long time that we built all these observatories 100 years ago, and they were, you know, kind of a few kilometres outside of the cities where they were.
Yeah, way out in the middle of the country. You know, a couple of k's out, a couple of miles out, in the complete darkness, no problem.
It was fine. Well, until all the cities grew up around them. Yeah. And that's happened in countless numbers of cities across the world. So we've had to shift all those observatories out into very, very remote places where we're fairly confident cities aren't going to expand into them.
But, I mean, remote places, when you say remote, you know, you can get out into the countryside here in the UK and be miles away from the nearest major city, but you are not miles away from the light pollution. You know, you can look in pretty much any direction and still see the glow from the nearest city. You've got to go a very long way, and that's becoming increasingly difficult to do.
Yeah, so astronomers in their observatories do have a lot of effort to preserve the night skies that they're looking at from a scientific point of view. But I think there's also a really important argument that we should, just as humanity, be looking after our night skies. So you see a lot of dark sky parks opening up. I mean, they're parks, but they're not sort of cut fences around them to keep all the night sky in, if you like. Instead, what they're doing in these places is restricting or controlling the amount of light pollution that we have. And this is light pollution that comes from things like street lights, from towns and cities. And do you really need those floodlights on your back garden all night long? High-rise
buildings which leave their lights on all night, even though there's only 3 people in the building.
Yeah.
All of these sorts of things. And I mean, you mentioned street lights. The design of street lights. They are slowly but surely getting better, but only if people take a conscious effort to do so.
Exactly.
The light from street lights, half of it's going straight up. It's madness.
Yeah, and so you can do things like shield street lights to push the light down, if you like, or build street lights at kind of street level, which is happening in some places to really stop all this, loss of. Because as soon as you put more light up into the sky, it becomes harder to see the stars. So there's all sorts of really interesting projects, and it's worth probably looking up to see whether there are any dark sky regions near you, and thinking about also how you can reduce the light pollution in your own environment as well.
It's a little bit like getting out into a wildlife preserve or a really good national park to get an appreciation for the importance of looking after the natural environment. Getting out into a dark sky area to be able to see what we're losing, to be able to see what we can't see around the cities, in the cities and around them. You can't see the staggering, just sheer enormity of the night sky. And I think we mentioned it before on this podcast. If you haven't been out into a proper dark place to look up at the sky, to see the enormity of that sky, then you got to do it for exactly the same reason why it's really important for everyone, if they possibly can, to get out and see the wonders of the natural world. You've got to get out and see the wonders of the night sky before we stupidly lose that forever. Well, we've come to the end of another episode of Syzygy, and I mean, it's been an interesting one. I think we went into the weeds, like we said, and perhaps didn't emerge as quickly as we thought we would, but that's okay. When you're on a topic like light, the nature of light, we could talk all day on this stuff, couldn't we?
Oh, love it.
So thank you so much to listener Stuart, who sent in that question. If you too want to ask a question, send us some comments, give us some feedback, just get in touch and say hi. There's a bunch of different ways you can do that. You can do that the way Stuart Priest did it, which was through the website, syzygy.fm. You can jump on there, have a look around, find all the past episodes, and then go to the contacts page. And there's a little form you can fill out, fling it our way, and we may feature your question on a future episode. We may turn the entire episode into a discussion of your question.
All about you.
Exactly, because it is all about you, the listener. But that's not the only way that you can get in touch with us. How else can they say hi, Emily?
Oh, well, we love Twitter.
Yes.
We're at SyzygyPod on Twitter. And you can see lots of little quick snippets and upcoming tidbits for the episodes that we're doing, and also some of the cool things that we enjoy out there in the Twitterverse. Tweeterverse?
Yeah,
the tree where all the birds sit.
That's right, out there on the Twitter tree, on our particular branch of the Twitter tree. The other place that you can find us in terms of social media, very exciting, we're on Facebook now.
We're on Facebook.
So if you're on Facebook, go and just search for us. I admit I don't even know how Facebook works at the level.
I have no idea.
You don't just sort of say we're at Syzygy Pod. On Facebook, go and find Syzygy Podcast. We're out there. You can find our webpage, links to all the good stuff. You can contact us through the webpage. That's another great way. The other thing you can do, if you're interested in listening to the show, you want to send it on to other people, look, we're available on all good podcast directories. You can find us in Apple Podcasts. We're now on Google Podcasts, which is very, very cool. All the other big directories. And we're also on YouTube. So if you like watching your podcasts, I know, a bit weird, but apparently the kids today are into this. YouTube's a bit of a thing. So all of our episodes are going to be going up there. And the great thing about that is that we get a little bit carried away. And by we, I mean I get a bit carried away each episode in finding images to go with the stuff that we talk about. Because astronomy is a very visual thing.
There is never a shortage of images. And not just like boring images like diagrams and things like... No. These are gorgeous, gorgeous images from all around the universe.
We do sometimes put graphs. Yeah.
Only sometimes.
Only if they're good graphs.
Yeah.
And some graphs are also... Anyway, point is, on YouTube, that's a visual medium, right? And so you're getting that enhanced podcast experience through checking it out on YouTube as well. But if you have a podcast player like Overcast on iOS or Pocket Casts, which show the chapter art on the podcast, then you can see those images on your phone as well. Anyway, that's
so
enough
modern.
of that. I know, it's crazy. But that pretty much brings us to an end of what we can talk about today. As ever, we produce this podcast in the offices here of the University of York in the wonderful, bright, sunny city of York. Very uncharacteristic, very strange. I'm not quite used to this. Here in Emily's office, which is always entertaining.
And next time we might have some interesting updates. So I'm going off on a conference next week to learn about updates from the Kepler and the TESS astroseismic consortia. So I will bring back for you the latest news on how TESS is doing and when we can expect to see some of the data, which is so exciting.
Very exciting. And one of the perks of the job. Not many perks about being an academic, but one of the perks definitely is travelling about the place to go to conferences. So we'll catch up with all of that next time. But until then, thanks for listening. Talk to you soon.
See you later.